Myself, Dr. Sachin Kumar, welcome you in my lecture of Module 3 Differential Calculus 2nd. Topic of my lecture is Partial Derivatives Part 1. In this lecture, I will discuss Introduction to partial derivatives of first order, partial derivatives of second order, problems of application of various order partial derivatives. So let us start with Introduction to Partial Derivatives. The concept of partial differentiation is applied for function of two or more independent variables. Partial differentiation is the process of finding various order partial derivatives of given function. Now, first order partial derivative. In this, we shall learn how to find out first order partial derivative of a function u equal to fxy of two variables x and y. First order partial derivative of u with respect to x is obtained by differentiating u with respect to x, treating y and function of y as constant, and is denoted by del u by del x. Similarly, first order partial derivative of u with respect to y is obtained by differentiating u with respect to y, treating x and function of x as constant, and is denoted by del u by del y. Now to understand it, we take example. If u equals to x square plus 2xy minus y square plus 2x minus 3y plus 5, then find del u by del x and del u by del y. Here we have given u equals to x square plus 2xy minus y square plus 2x minus 3y plus 5. To get value of del u by del x, we shall differentiate u with respect to x, treating y as constant. So del u by del x will be obtained by differentiating u partially with respect to x. We know x derivative of x square with respect to x will be 2x. When we shall differentiate 2xy, y will be treated as constant. 2 is already a constant, so 2y will be outside the differential operator, and the derivative of x with respect to x will be 1. So from this second term we shall get 2y as the resultant. Minus y square will be treated as constant, so its derivative will become 0. Differentiating 2x with respect to x, we shall get 2. So here we will get plus 2. The last two terms minus 3y plus 5 will be constant, so their derivative will be 0. So differentiating u partially with respect to x, we shall get del u by del x equals to 2x plus 2y plus 2. To find del u by del y, we shall differentiate u with respect to y, treating x as constant. Now we are treating x as constant, so derivative of x square will be 0. 2x will be treated constant, derivative of y with respect to y will be 1. So from this term, we shall get 2x as the first term of del u over del y. Now derivative of minus y square with respect to y will be minus 2y. So the second term will be minus 2y. Now 2x and 5 will be constant, so derivative of 2x with respect to y and derivative of 5 both will be 0. And differentiating minus 3y with respect to y, we shall get minus 3. So in this way, overall value of del u over del y after differentiating u partially with respect to y will be 2x minus 2y minus 3. Now, next we are going to discuss procedure of finding second and higher order partial derivatives of a function of two or more variables. If u equal to fxy be any function of two independent variables x and y, second order partial derivative of u with respect to x is obtained by differentiating u with respect to x twice in succession, treating y and function of y as constant each time, and is denoted by del 2u over del x square. Similarly, second order partial derivative of u with respect to y is obtained by differentiating u with respect to y twice, treating x and function of x as constant each time, and is denoted by del 2u over del y square. Here, if we differentiate del u over del y with respect to x, treating y as constant, then we get second order derivative of u denoted by del to u over del x del y. Here u is first partially differentiated with respect to y, then value so obtained, that is del u over del y, is differentiated partially with respect to x. Similarly, differentiating del u by del x with respect to y, treating x and function of x as constant, we get second order derivative of u denoted as del to u over del y del x. From the notation, it is clear that first u is differentiated partially with respect to x, then we get del u by del x. Now del u by del x is again differentiated with respect to y, treating x as constant. Here it is interesting to see that value of del to u over del x del y is equals to value of del to u over del y del x. In the similar way, third and other higher order partial derivatives can be evaluated. Now, to understand this procedure, we take an example. Find all first and second order partial derivatives of uxy equals to x raised to the power y. Hence, so that del to u over del x del y is equals to del to u over del y del x. Here we have uxy equal to x raised to the power y. Clearly, u is the function of x and y. Differentiating equation 1 partially with respect to x and y, we get. Now, if we differentiate u partially with respect to x, we shall treat y as constant. So, in RHS, x is a variable, y will be treated as constant. This case will be identical with derivative of x to the power n. And we know derivative of x to the power n with respect to x is n into x to the power n minus 1. So, applying this, here we get del u over del x equals to y into x raised to the power y minus 1. Similarly, if we differentiate u partially with respect to y, treating x as constant, then the function on RHS will behave like a raised to the power x, where a is constant and x is a variable. Since we are treating x as constant, so x will become constant and y will be variable. And we know derivative of a raised to the power x with respect to x is given by a raised to the power x into log a. So, differentiating u partially with respect to y, treating x as constant, we shall get x raised to the power y into log x as the value of del u over del y. Now, differentiating equation 2 partially with respect to x and y, we shall get value of del to u over del x square and del to u over del y del x respectively. To understand this result, we reach equation 2. Now we are going to differentiate equation 2 partially with respect to x. If we are differentiating it partially with respect to x, y will be treated as constant. Again, formula of x raised to the power n will be applied, and differentiating we shall get y into y minus 1 x raised to the power y minus 2. Again, if we differentiate equation 2 partially with respect to y, then we will apply formula of differentiation of product of two functions. Since y is the function of y and x raised to the power y minus 1 is also a function of y. So by product rule, we shall differentiate it. We kept y as such. Derivative of x to the power y minus y is done by the formula of a raised to the power x. So we get x raised to the power y minus 1 into log x. In the second term, we kept x raised to the power y minus 1 as such, and derivative of y with respect to y will be 1. So last term will result as x raised to the power y minus 1. Now, if we differentiate equation 3 partially with respect to y and x, we obtain value of partial derivative del to u over del y square and del to u over del x del y respectively. Okay, so to understand how del to u over del y square is obtained, we see equation 3. In equation 3, we have two terms, x to the power y and log x. If we are differentiating partially with respect to y, log x will be treated as constant and derivative of x to the power y will be x to the power y into log x. So on simplification, we shall get del to u over del y square equals to x raised to the power y into log x ka whole square. Again, if we differentiate equation 3 partially with respect to x, we have to apply product rule. So applying product rule, we shall get del to u over del x del y. First we differentiate x to the power y, whose derivative will be y into x raised to the power y minus 1 and log x is kept as such. In the second term, x raised to the power y is kept as such, and we differentiate log x with respect to x and get 1 over x. After simplification, del to u over del x del y becomes y x raised to the power y minus 1 log x plus x raised to the power y minus 1. From equation 5 and equation 7, it is clear that value of del to u over del x del y is equals to value of del to u over del y del x. So we take another example. If u equals to log 10x plus 10y plus 10z, then prove that sin 2x into del u by del x plus sin 2y into del u by del y plus sin 2z into del u by del z equals to 2. In this problem, we have given u equals to log of 10x plus 10y plus 10z. Clearly, u is a logarithmic function in three variables x, y and z. Differentiating equation 1 partially with respect to x, we got del u by del x equals to 1 upon 10x plus 10y plus 10z, since we know derivative of log x is equals to 1 over x. Also, if we differentiate 10x plus 10y plus 10z partially with respect to x, we get derivative of 10x as sec square x, while derivative of 10y and 10z will be 0, since both will be treated as constant. So in the value of del u by del x, we get sec square x in product. So overall value of del u by del x becomes 1 upon 10x plus 10y plus 10z into sec square x. Similarly, differentiating equation 1 partially with respect to y and z, we get del u over del y equals to 1 upon 10x plus 10y plus 10z. Here the multiplication is done by partial derivative of 10y, as 10x and 10z will be treated as constant. And value of del u by del z will equals to 1 upon 10x plus 10y plus 10z into sec square z. Derivative of 10z is taken in the product. The term 10x 10y will be treated as constant, so their derivative will be 0. Multiplying equation 2, 3 and 4 with sin 2x, sin 2y and sin 2z respectively, and then adding, we get sin 2x del u by del x plus sin 2y del u by del y plus sin 2z del u by del z equals to sin 2x into 1 upon 10x plus 10y plus 10z into sec square x plus sin 2y into 1 upon 10x plus 10y plus 10z into sec square y plus sin 2z into 1 upon 10x plus 10y plus 10z into sec square z. Now, putting value of sin 2x की value होती है 2 sin x cos x, and value of sec square x will be 1 upon cos square x. Both values will be in product. If we simplify these values, we shall get 2 sin x upon cos x, which will give us 2 tan x. So after simplification of first term, we shall get 2 tan x upon tan x plus tan y plus tan z in RHS as first term. In the similar way, second term will become 2 tan y upon tan x plus tan y plus tan z, and third term will be 2 tan z upon tan x plus tan y plus tan z. Taking LCM and simplifying, we shall get 2, as tan x plus tan y plus tan z will be in numerator as well as in denominator and will be cancelled out. Another example, if x equals to r cos theta, y equals to r sin theta, then find part A. derivative of x with respect to r treating theta as constant, and derivative of y with respect to theta treating r as constant. Also in part B, we require to find derivative of r with respect to x treating y as constant, and derivative of theta with respect to y treating x as constant. Here we have given x equals to r cos theta, y equals to r sin theta. So differentiating equation 1 partially with respect to r treating theta as constant, we got value of del x upon del r when theta equals to constant as cos theta. And if you differentiate equation 2 partially with respect to theta treating r as constant, we get del y over del theta equals to r cos theta. Now to get the values of partial derivatives del r over del x and del r theta over del y as shown in part B, we require to obtain value of r and theta in terms of x and y. For this, we shall firstly make square of equation 1 and 2 and both. If we did so, we shall get r square equals to x square plus y square. And if we divide equation 2 by equation 1, we shall get value of theta as tan inverse y over x. So differentiating equation 3 partially with respect to x treating y as constant, we shall get 2r del r over del x when y is kept as constant. Since derivative of r square will be 2r, and when we shall differentiate r with respect to x, we shall get del r over del x and y will be kept as constant. On RHS, derivative of x square will be 2x and derivative of y square will be 0. So on simplification, del r over del x when y is kept as constant will give x over r. Similarly, differentiating equation 3 partially with respect to y treating x as constant, we get del theta over del y when x is treated as constant. We know derivative of tan inverse x is equals to 1 upon 1 plus x square. So partial derivative of tan inverse y upon x with respect to y will be 1 upon 1 plus y over x ka whole square, and if we differentiate y over x partially with respect to y treating x as constant, we shall get 1 over x in product. After simplification, we shall get del theta over del y when x is treated as constant to be x over x square plus y square. In this way, we got values of all partial derivatives. Thank you.